Thank you, thank you. Thank you for the invitation. Thank you for staying until the end of the program. And thank you for the opportunity to talk about extrasolar planets. So I'm keenly aware of the time, so I will keep track of that so that hopefully we can stick to the schedule. So it's my pleasure to be able to talk about transits and their relationship to extrasolar planets. And as was already mentioned, the detection of planets by almost every citizen science is now a regular possibility simply because of the advance of technology. And this is one of the things I wanted to focus on. You may recognize Mabdi Rahman in the corner of this photograph. He was a TA for a upper division undergraduate class at U of T here last semester. And this group of students is responsible for one of the lab exercises in which we detected an extrasolar planet. This is GJ 436b. And you can see the characteristic signal in this light curve. This is time in hours versus brightness normalized to the mean brightness. And you can see the scale here. This is a very fine scale. This is 0.5% variation, indicating in this particular object the detection of a Jupiter-sized planet orbiting this star. So before I talk about that, I want to talk more generally about detection of planets. And of course, you can do this just around sunset this evening. This is the skyline from Toronto this evening at about 9 o'clock. The sun has just set over here in the west. Maybe you've been following Venus. And in fact, we have a great display right now with Venus. We have also Jupiter is over in the west, and also if you look closely here, there's also Mars directly overhead, and Saturn. So in fact, with the exception of Mercury, all the planets known in antiquity. And the point I'm trying to make here is that technology is something that's changed our perspective, changed our sense of scale in the solar system, from prehistory out to the orbit of Saturn at 10 astronomical units. With the invention of this remarkable and very simple device, this is Galileos Telescope, literally overnight, the scope of our own solar system increased by a factor of 3. Let me explain how it is. Here's a famous picture from Galileo's notebooks. Like all good astronomers, he's up at 3 o'clock in the morning. This is 3:46 in the morning, December the 26th. A remarkable year, another golden age for astronomy, 1612. And I've drawn up a little key here that shows Jupiter and what we now know as the Galilean moons, which of course is in itself a remarkable discovery. And then not realized until sometime later, actually in the 20th century, this object that he has denoted as a star is in fact Neptune. And so the universe expands by a factor of 3, although of course the realization took some time. We're in a phase of exponential growth of the discovery of extrasolar planets. This chart only shows the last couple of decades, and the largest column in this histogram, 2012, of course, is incomplete. This is up to date as a few days ago, and the doubling time for the discovery is a few years. The reason that this explosion has happened is for the deployment of 2 techniques for discovering extrasolar planets. They're both indirect methods. That is, you don't see the planet itself, you see the influence of the planet on its host star. The one that was deployed first is the Doppler method, which sees the reflex motion as the star orbits the planet. So you see the characteristic Doppler shift of absorption lines in the star's photosphere. And the one that we've been talking about today, the dimming of the integrated light from the star. So you don't see the shadow of the planet on the stellar disk itself, but you see the integrated reduction in light, as I showed you in that very first slide. So this is a very simple technique conceptually, but vast amounts of information have been extracted from the light curves measured. The primary reason for that exponential growth in the last couple of years, launched in 2009 a dedicated observatory, which is a space observatory, so it gets to observe all the time. It has a large field of view, and because of its location in space is uninterrupted. The principal features of this observatory is large collecting area. The entrance aperture is almost a meter in diameter, and then the sensing device, the camera in here, encompasses almost 100 square degrees with this sophisticated array of CCD sensors. And showing that in context, here's the rocket, here's the Delta launch in March 2009. This is the field that the Kepler satellite stares at continuously. You can see the arc of the Milky Way running through the constellation Cygnus. It looks a little bit off the galactic plane because looking right on the galactic plane, there would be too many stars. Looking close to the pole, would be too few. And there's 100 square degrees, as Jay mentioned, there are hundreds of thousands of stars that are continuously monitored for these periodic dips that betray the presence of an extrasolar planet. In context of the Milky Way galaxy, we're looking at a tiny little fraction of our own Milky Way. So when I show some of the results, you need to extrapolate this beyond our solar neighborhood to the entire galaxy. I'm going to show you a gallery of several planets that have been discovered by Kepler. This is a triple system, and this is one of the remarkable things that Kepler has shown us, is that systems with multiple planets appear to be common. Shown at the top is a light curve. You can see modulation in the light curve. This is brightness versus time in days. Modulation due to rotation of spots in this particular star, as well as some systematic errors. You see discontinuities in the light curve due to processes in the spacecraft. When it's corrected, you see that the light curve is interrupted, apparently at random at first, by drops in the brightness, and these occur as the 3 planets in this system pass in front of the star. The information that's encoded in this tells us about the solar system. There's 2 basic pieces of information here. First, the periodicity. For example, if you look at the red dot, that shows you the period of the planet that's encoded with a corresponding symbol. So there's the period, but there's also the depth of the eclipse. And so when you look at these light curves where they're added in synchronism with the eclipses, you can measure how deep they are, and that tells you what the relative area of the planet and the star is. That is, what's the radius of the planet. The increase in the number of candidates has been startling. This is another way to visualize that information. I love the picture that Jay showed, that was an album of all the catalog candidates from June through February 2012 through the most release. Here's another way of visualizing it. There are about 2,300 candidates. Most of them are Neptune-sized objects. There are some Jupiter-sized objects, some super-Jupiter objects, and perhaps, maybe somewhat parochially, some of the interesting objects are the Earth-sized and even sub-Earth-sized objects. The record so far for the smallest planet is as I'll show you in a minute, is a Mars-sized object. So this is maybe a rather dreary rendition of the statistics showing orbital period. This is perhaps one thing to be aware of, is that the periods are rather short periods. So on this scale, the period of the Earth, 365 days, here's 100, 200, 300. So the Earth's period is, orbital period is here. These are all inner solar system planets from our perspective in these systems. But the size of these objects span the entire range from Earth-sized objects, Neptune-sized objects, Jupiter-sized objects. Here's a wonderful picture that is created by my colleague, former colleague at the University of California, Dan Fabrici, that the word orrery may conjure up visions of wonderful brass mechanisms. This is a digital orrery showing just the candidate planets with more than one system. And I have to show you that again because it's such a wonderful picture. And maybe it will, maybe it won't. There it goes. So I should just stop here because anything else that I say after that picture is underwhelming. But let me just show you a few of the interesting objects that have turned up in this planetary zoo. So Kepler 11, so when you see a designation Kepler number, that means it's a confirmed system, not just a candidate. And Kepler 11, if you look at the dots here that are producing these periodic transits, there are multiple planets. There are 1, 2, 3, 4, 5, 6 planets in the system. They're all relatively small, Neptune to Earth-sized objects, and the largest one orbits just outside, if this were our solar system, just outside the orbit of Mercury.
What is the scale of the diagram?
So the radius of this outer planet is just beyond the orbit of Mercury. So these are astronomical units. So I have a version of this that visualizes this information in a graphically interesting manner, which shows the orbital scale. The star observed from a distance, you can see, is flickering due to the occultations that are occurring, and then the perspective will zoom out above the orbital plane, showing the closely circular orbits that are present in the system. So again, the information you get is how big the planets are relative to the star, that is their radius relative to the radius of the star, and also the size of the orbits, and with careful monitoring, also the eccentricity of the orbits. A planetary system that perhaps is most interesting because nobody thought that such things would exist is known as Kepler 16b. This is a planet, this is a Jupiter-sized planet that orbits a pair of stars, a K-dwarf and an M-dwarf. The orbital period of a stellar system is about 40 days. The orbital period of a planet is about 200 days. And so it orbits outside the orbit of these two stars, orbits the common center of mass of those two stars. And again, an imaginative animation based on the measurements showing the relative scale of the system and the orbit relative to the two stars. And those of you who are aficionados of the Star Wars series may recognize the reference to the name of the planet is often called informally Tatooine. So as I indicated, the primary interest is perhaps in finding the smallest planets that are comparable to our own, that is planets with densities that indicate that they're made of rock. If you have both Doppler information and the transit information, you can infer not just the size, but also the density of the planet, and therefore what it's composed of. So far, there is not an identical twin of Earth that is a rocky planet at 1 astronomical unit from a solar-type star where liquid water could be present, but it's clear from the progress in this field that it's not, this is not very far away. Here's a number of confirmed planets in the Kepler system that are Earth-sized, plus the record holder for the smallest planet that's currently known. This is KOI, stands for Kepler Object of Interest, and KOI 961 has 3 extremely high confidence candidates, the smallest which is Mars size. So when Mike mentioned looking at transits and understanding whether the planets had rings or even moons, that is something that's very close to being on the horizon, as well as understanding whether there are terrestrial direct analogs. So this one that I just mentioned is literally the smallest system and has remarkable scales. The actual size of the objects are not to scale here, but the orbital radii looks much more like a Galilean moon system than indeed a solar system. So I think the most important thing to take away from this part of the talk and what we've learned so far from transits is that small planets are numerous. This chart represents a statistical analysis of the number of planets. So this is a histogram versus radius. So 1 Earth radius is here. And you can see as you go to smaller and smaller radii, the probability that a star has a planet is increasing such that if you extrapolate this, and this region is incomplete because of the reduced sensitivity to smaller objects, certainly it seems like terrestrial planets are abundant in the sense that almost 10% of stars have terrestrial planets. How many of those are in habitable zones? We don't yet know. So in my remaining few minutes, I'm going to extrapolate to the future, remind you that, again, these are indirect methods. Much of what I've shown is entirely quantitative in terms of the orbital properties, the sizes and densities, but we're not taking pictures of planets yet. And also, despite that very exciting histogram that showed in the latest date bin lots of planets, if you replot this histogram, not now in terms of date, but in the orbital separation, this is in semi-major axis, here's where Jupiter would be, out to the orbit of Neptune. Most of the planets that have been discovered so far are crowded into these inner regions where indirect methods such as Doppler and transits are very effective. We haven't begun to explore the outer solar system regions of our planets. And as perhaps you know, some of the most interesting aspects of our own solar system are only revealed at large distances. So in this representation, the circles represent the orbits of the outer planets. So here's Jupiter, here's Uranus and Neptune. This poor little circle here is Pluto. It doesn't get a circle because it ain't a planet. And in the domain of Pluto, out at 40 to 50 astronomical units, this is the domain of the Kuiper Belt objects, which are the kin of Pluto. And since we're talking about transits and eclipses, I thought my talk would not be complete without an eclipse photo. This is the 2008 total eclipse photograph from Mongolia, and a wonderful high contrast composite of this same eclipse. So in the previous picture, you can see some planets, or at least you can in the original. And if you look very closely right here, Mercury and Venus, and in this somewhat smaller scale, here's Venus. The reason I wanted to show you this is, this is Mercury. Mercury is 2 billion times fainter than the sun. You need to somehow obliterate the light from the sun so that you can see Mercury during the daytime. But just imagine Mercury now orbiting one of these planets. This is the Praesepia beehive cluster in the background. Imagine Mercury orbiting one of these stars in the background. Put it, the nearest stars are 100,000 times further away than the sun, so it's 100,000 times closer. And also, since brightness goes inversely with distance squared, it's now 10 to the 10 times dimmer. You can imagine it's extraordinarily difficult to see planets orbiting nearby stars. You need extraordinary contrast. And this rather amusing picture from National Geographic characterizes looking for an extrasolar planet in direct imaging is looking at a Firefly with its milliwatt power next to the many kilowatts of power from a searchlight. So it is possible, though. One of the replacement cameras on the Hubble that was part of a servicing mission in 2002 specifically had a coronagraph to produce artificial eclipses. A candidate solar system that's been known since the mid-'80s is the bright A star in the constellation the Southern Fish, Alpha Piscis Astrinus, or this is Fomalhaut. If you take a picture of Fomalhaut with Hubble Space Telescope, it looks like this. Maybe not surprising. It's a first magnitude star. But if you take a picture of Fomalhaut and then an image of another bright A star, in this particular case, the A star Vega, and subtract the two, you can make a picture like this that shows in the middle, and maybe this is the telescopic version of retinal eye damage. The image sensor in the Hubble has been completely saturated. Thankfully, there's no permanent damage. But these pixels contain no useful information and have been blacked out. But arcing through this image, there is a belt of light that is dust orbiting the star Fomalhaut that's right here, and is scattered starlight from the belt from the star to the belt to our line of sight. And those with keen eyes will notice in this 2004 picture a little dot here, which at the time we had no idea what this thing was. It could have been a background star. It could have been an artifact, but in images 2004, 2006, it moves on an orbit, and we've recently imaged it again just a year ago, showing a third epoch as it orbits inside this belt of dust. So this is one example of imaging a planetary object in a planetary system. So this ring of dust around Fomalhaut is like our own Kuiper belt, or at least the dust from our own Kuiper belt. Another star that was imaged now from the ground using a technology called adaptive optics has a rather uninteresting name, HR 8799. This is a planetary system where, again, the planet has been occulted, as a star's been occulted in an artificial eclipse using a coronagraph with 1, 2, 3, 4 planets, which are all moving according to Kepler's laws of motion. And because we're not content with our current technology, we're designing adaptive optic systems. These are ones that correct for the twinkling of the Earth's atmosphere. A particular instrument I'm working on will be delivered to the Gemini South Observatory in northern Chile early in 2013 in February, and we'll begin a planet hunting campaign to take more images of planets. And of course, we're on the route to building ever bigger telescopes. This is the current major Canadian project, which is a 30-meter telescope. The largest ground-based telescopes are now 8 and 10-meter telescopes. And this will be an extraordinary facility for finding even more planets. And then just to wrap up, I wanted to share with you the final evidence that extraterrestrials know that there is intelligent life on the Earth. This is a picture taken in California, just south of Stockton, a town of Lathrop. And you'll notice there's a cornfield here. And as we zoom, this is on Google Maps, as we zoom into this cornfield, you see there's a maze has been cut into this cornfield. And when you look very closely, ET will discern the Kepler 11 system here that I showed you first, with its 6 planets being observed by the NASA Kepler satellite. So in that respect, you can expect that our galactic neighbors will be coming and paying a courtesy call sometime soon and share their knowledge of transits of extrasolar planets. Thank you. Oh, so the 30-meter telescope this is an international project. It involves the US, Japan, China, India, and the site that's been selected for that is on the big island of Hawaii. So it's right in the middle of the Pacific. So obviously a good place for eclipses. And
when you have a star that's rotating around another star, does it transit across? I mean, they cross each other. So can you tell in the same sort of way using? Sorry, I'm not an astronomer. But does it change do the stars affect each other in the way that a planet travels?
Oh, absolutely. You know, the techniques used for understanding these transits of extrasolar planets were all initially developed for studying binary stars, and so the math and the physical understanding is just as derived from that. So you see exactly the same phenomenon. Of course, if you have a pair of stars, they're both luminous, yeah. and so but they invariably are stars of different temperatures, and so you see brightening and dimming depending on the relative temperatures of the two stars in their relative areas. And in cases where the planet is very close to the star and is heated by irradiation from the star, then you can get you see also phenomena that are common from binary star eclipses.
What we're seeing is what transits that we can see with transits. So what percentage of that is that of what possible planets are there? Because there's obviously ones that are going to have orbits. So
Absolutely.
Like 5%?
Absolutely. You know, the fraction of the sky covered by the planet during its orbital course around the star is a tiny fraction of the solid angle of the sky. So the typical probability of seeing eclipses is very small, 1% or less, depending on the exact geometry.
So we can say like 100, there's actually probably...
So this is a tiny fraction. These are just the lucky ones. And of course, these are very interesting planets because if I watch a transit occur on a distant solar system, that transit, of course, the plane of the orbits are such that ET sitting on that, it knows that we're here. Jay.
Well, it's been exciting for me to be here today, and I've met a man who discovered a planet around Fomalhaut and some others. I met Ian Shelton, who discovered a supernova, so I'm really enjoying myself. Now, we do have, as you said, as indicated earlier, some thousands of these candidates and KOIs, Kepler objects of interest. I'd like to hear what you have to say about things we might discover at transits of Venus or Mercury in our solar system that would help you distinguish the real ones from the candidates.
Oh, I think, well, I guess I have higher confidence regarding the statistical interlopers in the Kepler catalog. There's been several recent reanalyses that indicate that the Kepler candidates already have been winnowed to a degree that there's a very large likelihood that all those just are real planetary systems. But I think the real interest, of course, is the thing that I didn't get a chance to talk about, which is understanding atmospheres. And of course, if you want to understand atmospheres, the principal method is going to be transit spectroscopy, that is using the star as a background illuminating source to illuminate the atmosphere. And I thought those pictures that you showed us of the Venus atmosphere illuminated during transit were truly spectacular and very helpful understanding the physical phenomena. So that would be the thing that I would want to know more about.
Thank you.
Okay, thank you.